So let's talk more about the design generator. In fractional factorial experiments, the interaction term that divides the test runs is referred to as the design generator. And table 1430 in your book shows the design generators for a bunch of different fractional factorial designs. It's typically a higher order interaction term. In fact, for half fractional factorial designs, the best design generator is the highest order interaction. In the last example, the design generator was I equals ABC. And again, we can get all sorts of different things from this I equals ABC. If we multiply both sides by C, we end up with C equals AB, as I showed. Based on the definition of the design generator, all of the aliases, or the aliasing structure for a given fractional factorial design, can be determined using simple algebra. For example, since A times I is just equal to A, and A squared is always equal to I, we can do the following math. If we start with our design generator, if I wanted to calculate the main effect of A, I can just multiply the left side and the right side by A. A equals A squared times BC. A squared equals I. So in the end, we can get the aliasing structure for A. A for this design is aliased with BC. And you can do the same for every effect in this design. Let's take a look at a more complicated half factorial design, the 2 to the 4 minus 1 design. And there's kind of a shortcut here for creating these half factorial designs. The first step is to start with a 2 cube design here. So 2 to the 4 minus 1 you can think of as you can start with a 2 cube design. And so we set up ABC just like we would for a full 2 cube design. The next step is you add the fourth factor, aliased with the highest order interaction of the 2 cube design. For a half factorial design, that's D equals ABC. We got the design generator I equals ABCD from that table, which leads us to D equals ABC. That means in order for us to determine whether or not D should be at the low level or high level in these 8 different experiments, we can just calculate that by D equals the product of ABC. That's easy to do in Excel, so we can easily calculate this column of the coded variables for factor D. For a 2 to the 4 minus 1 with I equals ABCD, the aliases are A equals BCD, B equals ACD, and so on. If you want to calculate the binary effects, you just multiply the left side by whatever binary effect you want to find. So if you want to find AB, you can just multiply both sides. AB times AB is just I, and so we end up with AB equals CD. And so we can easily determine the aliasing structure using simple algebra. Taking a look at the aliasing structure, if ternary effects are negligible, which is usually a good assumption, this design will be effective at determining the main effects. For example, the main effect B is aliased with ACD. That means if we determine that this combined B ACD effect is significant, it's most likely that that significance is due to the main effect of B, because the significance of ternary interactions is usually small. This type of design is known as a resolution 4 design. In other words, where the main effects are not aliased with each other or with binary effects, but the binary effects are aliased with each other. That's known as a resolution 4 design. You can gain or add resolution to the design based on what you're looking for. There's a resolution 3 design. This means main effects are not aliased with each other, but the main effects are aliased with binary effects. And that was our 2 to the 3 minus 1 example from earlier. A resolution 4 is the one I just talked about. The main effects are not aliased with each other, nor with binary effects, but the binary effects are aliased with each other. And a resolution 5 means that no main or binary effects are aliased with each other. Binaries are aliased with ternary effects. The resolution 5 design requires the most number of experiments, but yields the highest resolution. Let's take a look at a quarter fraction design. This is useful when the number of factors gets quite large, so greater than 5 factors. An example is a 2 to the 6 minus 2. The shortcut, we start with a 2 to the 4th design in A, B, C, and D, and then we add 2 columns for E and F based on the high order interactions of A, B, C, and D. E is equal to ABC, and F is equal to BCD. Why did we choose these when there are so many different choices? Well, you can get these design generators from table 1430. The design generators have been worked out so it guarantees the best resolution of the main effects. And so that's how we got these columns. In order to determine which combinations of E and F to use, we just multiply A, B, C to determine E, and we multiply B, C, and D to determine the level that F should be run in for each of these experiments. As I just mentioned, from table 1430, we can get the design generators for the 2 to the 6 minus 2 design. These are the design generators. We can rearrange these to the following by multiplying the left one, the first one, by E, both sides by E, the right one multiply both sides by F, and these are two equivalent design generators. Now, because I is equal to I, we can say that ABCE is equal to BCDF, and both are equal to I. And there's one more that we can create. If I multiply both sides of this left one by BC, we end up with BC equals AE. And if we substitute this BC into here, we end up with I equals ADEF. And so that's another alias here I can put for I, ADEF. Here we have 4 different terms that are equal to each other. The difference between K and P here, if you take 2 to that number, that's equal to 4. That's how many terms should be equal to each other. So for example, a 2 to the 7 minus 4 design, we should have 2 cubed things that are equal to each other in order to put together the complete aliasing. So now if I wanted to determine, for example, what is A aliased with, I can just multiply A by any of these terms because they're all equal. A times I is equal to A, and then I would get A squared, which is 1. A is therefore aliased with BCE. And then the third one here, A would be aliased with ABCDF. And then A, if multiplying that last one, would be DEF. So this is the aliasing structure for a 2 to the 6 minus 2. A is aliased with these 3 other interactions, and you see that A is aliased with only 3rd and 5th order interactions. Let me show you how we can do this in Minitab. Minitab will actually allow us to design a fractional factorial design, and we can also get the aliasing structure. So I'm over here in Minitab. We can go up here to Stat, DOE, Factorial, Create Factorial Design. Now we're going to do a 2 to the 6 minus 2. We have 6 factors. If you're interested in looking at the resolution and the different designs, you can click on Display Available Designs. And here we have for the runs required, we have the factors and the resolution. So we're going to change this design to a quarter fraction. This is 2 to the 6 minus 2. The resolution is 4. It requires 16 runs. We're going to go ahead and click OK. And another thing I want to do is I want to deselect randomized runs. So I can select OK. We can click OK again. And it's going to go through and it creates the table of runs that we need to do. And this is exactly what I showed you how to do earlier. Now the nice thing about Minitab is it gives you the aliasing structure. All of these 4 terms, for example, in each row are aliased with one another. I showed you how we did that by hand. A is aliased with BCE, DEF, and ABCDF. So this is a much easier way to get the aliasing structure. And you see that all of the main effects are only aliased with 3rd and 4th order terms. The statistical analysis of these fractional factorial designs is a little more complicated. We still compute contrast, effects, and component sum of squares. The equations and formulas are a little bit different. We have a P in the exponent here in the denominator for the effect equation and the sum squared of that effect. It's typical to create normal scores plots of the effects, also known as normal effects plots. We can use ANOVA. We can use regression analysis. We can analyze our residuals. And this is all best illustrated through a workshop. You'll be performing the statistical analysis of a fractional factorial design in an upcoming workshop. Thanks for watching.